I'm Professor Brad Fulton, and welcome to my Stats podcast. This is an edited audio recording of my course. Each lecture is its own episode, and there's a total of 24 lectures. This course provides an introduction to the quantitative methods social scientists and data analysts use to collect and evaluate empirical data about society. Through this course, you will learn to gather, describe, and analyze data with an emphasis on the application and interpretation of these methods. This course will also help you to be a more informed and critical reader of academic research, public opinion polling, and advertisement claims that present statistical evidence. Although some of the current events I reference might be dated, the content is timeless. I hope you enjoy this lecture, and if you have any questions, you can email me at bradrfulton@gmail.com. Hi, my name is Professor Fulton. If you like this podcast, you'll love the book I use for the course. It's titled Statistics, Unlocking the Power of Data. This book uses a highly intuitive approach to help students visualize statistical concepts, which accelerates understanding. I've reviewed dozens of textbooks, and Unlocking the Power of Data is hands down the best one out there, mainly because of its unique intuitive approach and straightforward explanations. You can find a link to the textbook in the show notes, and if you use the promo code BLOCK5, you'll get a 10% discount. We know what population is, but then parameter, just like sample statistic, you don't usually talk about that. We talk about samples when we talk about statistics, but what's a sample statistic? So population parameter is the thing that you're interested in, either like the proportion, the mean. Those are the predominant parameters that you're interested in, is either the proportion of people who believe something or the mean height of people. So parameter is just a general term for things like mean or proportions. And that's ultimately what we're trying to find with this analysis, is the population mean or the population proportion. And the way that we find that in statistics is by taking a sample of the population, and from that sample we get a sample statistic. So we get the sample mean, and then from our sample we can infer what the population mean is. If we wanted to know height of all the people in Durham, so we did a random sample of 100 people in Durham and found out that the mean height is 5'10" inches. That's our sample statistic. And then if we wanted to have an estimate of what the population mean is, the only number that we have is our sample mean. So that actually is our estimate of the population mean, 5'10", but we know it's just an estimate. So that's why we do confidence interval. We're like, well, how confident are we in our estimate? So in many ways, the sample statistic becomes our estimate of the population parameter. So it isn't like you do one set of calculations for the sample statistic and then forget that and then say, okay, now let's figure out population parameter. It's actually you use all the information in your sample statistic to estimate your population parameter. And I say the word estimate because it's an estimation of what the population mean is based on our random sample. Looking at just visually, the population mean is going to be at the center of the distribution. So what that distribution shows is 1,000 different samples. There's going to be variation in our sample statistics. So every sample you do is going to be slightly different. You know, if I did 100 people in Durham one day and then I did another 100 people, it's going to be slightly different. It's not going to drop down to 4 feet. It's going to be like maybe 5'9" inches. But on average, the center of that distribution is going to be what our population mean is. We're going to be referring back to stuff from part 1, but it's going to also be then building on that. A couple of things to clarify that popped up on the assignments, that the z-score is not the same as a percentile. And I can see from the assignment where that might have been confusing because I think the z-scores were 0.74, 0.8, and 0.98. And so it was natural to think, oh yeah, 0.98, that's the 98th percentile. But the z-score is the number of standard deviations above or below the mean. You guys are right in that it's a measure of location. Chris might get this one. If the z-score is 2, what is the percentile?
95%.
95th percentile, because we know that this is sort of one of those known points, is that if you're 2 standard deviations above the mean, you're at the 95th percentile. If your z-score is 1.7, we don't know that right off the bat. You have to look that up. But you can know that if you're 2 standard deviations above the mean, you're at the 95th percentile. So a z-score of 0.98 does not equal the 98th percentile. What would a rough estimate of a z-score of 0.98, a rough range that it would be in? Brittany?
66.
66. And how did you get that?
It's close to 1.
Uh-huh.
And like 1 standard deviation is like 66. I don't know.
Yeah, that's even better. So I was just going to say it's less than 2, so we know that it's going to be less than 95, but it's greater than 0, so we know it's going to be greater than 50. If the z-score was 0, that means you're how many standard deviations from the mean? 0. So it means that the location of that score is right at the mean. It's, in a sense, at the 50th percentile. Part 2, this is a tricky one, commonly trips up people and seems to be tripping up you guys, is that some variables appear to be quantitative, but they are really categorical. One common one is year born. So year born, you would say 1990. Although that seems like a quantitative, if you wanted to find the mean value for year born, it would be taking all these years, like 1990, 1985, 1997, and the mean value would be like 1992. But what you're really interested in is how old the person is. Or like income bracket, a lot of you guys are picking the variable income, and if you look at that variable, it has 12 categories, and the categories range from like really, really low income to not so low income, and the highest category is $25,000 or more. And so you have like a ton of people in that category, and so you really don't have a continuous measure of income. You really have a categorical variable that has income brackets. And it's not a very good one because it only is showing the income brackets of the really, really low income, and then it just lumps all of the high income people into one category. Another one is occupation code, and it gives a number, but that number is in reference to some type of occupation. You know, someone had put it down as a quantitative variable, and then they found the mean value. The mean value was 122. Sure, it's a number, but what does the mean occupation code mean? It doesn't have any meaningful information because occupation code is really a categorical variable. So as you guys are walking through this and looking at your variables, make sure that the quantitative variable really is a quantitative one. Good quantitative variables include phrases such as how many, how often, and the respondent answers with a number. That's a good self-indicator of the quantitative variable. And then another thing to be aware of is who was asked the question. Was it everyone in the sample or a subset of the sample? So I think one of the questions is, what's your Jewish denomination? So you can either be Orthodox Jew, Conservative Jew, Reform Jew. You can see that not all of the people were asked that question. If you look at that variable and it says that 30% of the people are Orthodox Jew, you couldn't say that 30% of the American population is Orthodox Jew. You could say that 30% of Jewish people are Orthodox. Be aware of who's asked the question, because if you're going to make an inference about the population, you need to know which population you're talking about. Brittany?
I had a question on part 2. And
Yeah.
something. There were certain variables that I would try to run against each other that wouldn't provide results.
Okay.
There would just be dashes instead of coming up with an R value, or I get a screen that says like these two variables are not.
So one reason why that might be is this is a survey that's been done since 1972. And every 2 years, they run the survey. They sample roughly 1,500 people, and they ask them a set of questions, and then they load this data onto the website. And then in 1974, they grab another 1,500 people, ask another set of questions. Some are the same questions that they asked in 72, but some are new questions that weren't asked. And then that process continues. And so it's not the same people every year. It's a different sample, a different random sample. And so if you picked a variable that was only asked in 1985, you only have data points from that variable for the people in 1985. And say you try and compare it with a variable that was asked only in 1990, The variable needs to be in both surveys.
Oh, okay.
In order for them to compare, because when you do correlations, it's always looking at a person and two characteristics of that person and how they relate to each other. So that could be one of the reasons. We'll move on to the second part of confidence intervals as a part of understanding inference, and this is going back to, we have a sample mean or a sample statistic, and we're trying to make an inference about the population from that sample statistic. How confident are we in that inference? So summary from last class. So to create a plausible range of values for a population parameter, we take many random samples from the population and compute the sample statistic for each sample. We each took a random sample from the bag of Reese's Pieces and generated a sample statistic, and we took all those sample statistics and put them into a sampling distribution to get a sense for how much variation there was in our sample statistic. And then we compute the standard error, which is the standard deviation of all these statistics. Remember when we had the chart right here with all the dots, and then we look at that distribution and we say, okay, what's the spread of those values? That standard deviation has a special name. It's called the standard error. So the standard error is the standard deviation of your sample statistics. And then we can calculate the plausible range of values. It's the sample statistic, take like Timothy's sample statistic, and then we do plus or minus 2 times the standard error for the distribution of sample statistics. Which step in this process is the most confusing for you guys?
When you say compute the sample statistics for each sample, is that like...
The sample statistic? So the sample statistic is you have your sample, and if it's a quantitative variable, you want to know the mean value for all those variables. And if it's a categorical variable, the proportion. So quantitative variables, the sample statistic that we're most interested in is the sample mean. If it's a categorical variable, the sample statistic that we're most interested in is the proportion. For others, what's the most confusing step in this process? Brittany?
I think I was getting confused when I was trying to computing the standard error and then the plausible range of values.
So the plausible range of values is the same as the confidence interval.
Mm-hmm.
And the sample statistic is the statistic from one of your samples. Even though we took 100 samples, we're just going to take one of them, and that's why I said we'll take Tim's, and his sample proportion was 0.5. And so then we insert 0.5 right here. So that's our point estimate of the population. But then to get the confidence interval, we need to do plus or minus 2 times the standard error. And the standard error is looking at the sampling distribution. For the sample statistic, you look at one sample.
Yeah.
For standard error, you're looking at the distribution of all sample statistics. Okay, so there's one small problem. This would work beautifully, but the small problem is that often we only have one sample. So almost all of these studies that you see or that we do, or even in the GSS, they have one sample of 1,500 people. And so all they have is one sample statistic. They're not able to find out the variation in that sample statistic. You know, what we did yesterday, we had 6 of you, so we had 6 samples, and then even when we went on the computer, we could do 1,000 samples. And so we could get our distribution of sample statistics. But in the real world, you typically only have one sample. And so then how do we find out this information if we don't have a sampling distribution? So that's the theme or focus of today. To restate the problem, we have one random sample of the population. We need multiple, greater than 1,000 random samples from the population in order to calculate the standard error of the sample statistic. We can't afford to conduct 1,000 plus random samples. So is there a way to use the information from the one random sample we have to simulate 1,000 plus random samples? Yes. Do you think it's easy or confusing?
Very confusing.
Did anyone read the stuff on Bootstrap? You tried, okay. So it is going to be mind-boggling, but it's been tested and it works and it's true. So I'm going to try, I've read the book and I see how they explain it and they do a great job. And instead of reiterating what they say, I'm going to look at it from a different angle and see if that can work. The bootstrap simulation method enables us to generate a sampling distribution. A random sample of a population is equivalent to the population. And that's assuming that your sample size is sufficiently large. So if I just took a random sample of 6 people, that wouldn't necessarily be equivalent to the population. But if I took a random sample of 500 people in Durham, in fact, I was on jury duty about a month ago, and it's crazy. So you show up to jury duty, and there's about 100 people in the room, and they're all from Durham. And I looked around, and the way that you get selected for jury duty is basically if you're between 18 and 88, they randomly pick your name out of a hat. So it's a random sample. So I'm sitting in the room with 100 people, and I just look around, and I'm like, it works! I mean, I saw all different ages, all different ethnicities, a mix of gender, a mix of education level, a mix of income level. I mean, it was like unbelievable. I was like, this is a random sample, and this is actually a snapshot of Durham right here in this room. And even though it's only 100 people and there's, I don't know how many thousand people in Durham, but just in that one room was basically the equivalent of the Durham population as far as characteristics and features and demographics. So a random sample is equivalent to the population. So when we conducted our study yesterday, we had our bag of Reese's Pieces. I'm going to walk through this. You won't even fully understand this as I walk through this, but at least you'll have the slides to reread through the logic of it. We treated this bag of Reese's Pieces as the population, and we drew random samples of 10 from this population. Here's the 500 in the bag, here's the 10 we drew. What if our sample size was 500, which is the total number of pieces in the bag? We would know the exact proportion of orange pieces in the population. If I went and counted all these, which I actually did, there's 260 orange pieces in here. The proportion is 0.52. So we would know what the proportion of orange pieces in the population is. So then, is the proportion of orange pieces in this bag pretty close to the proportion of the entire population of Reese's Pieces? So the entire population is if you go to the Hershey factory and there's over 1 billion Reese's Pieces. Do you think that the proportion that's in this bag is pretty close to the proportion that's at the Hershey factory? Okay, you guys would say yes. What type of sample is this bag? A random sample. Perfect, Chelsea. So because this bag is a random sample of this big population, it's more or less equivalent. So this bag looks, in a sense, just like the large population because it's a random sample of this large population. So then, because this bag is a random sample of the entire population, it contains approximately the same proportion of orange Reese's Pieces as the population. Whatever proportion we find in this bag is going to be more or less the same as the proportion in the population. So our goal is to determine the population proportion of orange pieces. Let's say that we've determined that a sample size of 500 is sufficiently large enough to adequately estimate the population proportion. And this bag we have right here is the one random sample. We're trying to estimate the total population proportion of orange pieces. And I could go out and buy 1,000 bags and count it every time. Can't afford to do that, so this is our one sample. And so then it gives us one sample statistic, which is 0.52. That's the proportion that's in this bag. But we need multiple. Can't afford to buy 1,000 bags. What we can do is use this sample to generate multiple samples. Drawing additional samples from this bag is equivalent to drawing additional samples from the vat of Reese's Pieces at the Hershey factory. So if I said, well, we need to draw 1,000 more samples of sample size 500, we can either go to the Hershey factory and reach in and grab 500 Reese's Pieces, carry them back, spread them out, count them, or reaching into the vat at the Hershey factory is equivalent to reaching into here. Because they're equivalent, it doesn't matter whether I reach into the factory or I reach into this bag. So I could reach into this bag and pull out another sample of 500. Chris?
So would like 100 be too low for your random sample for like this kind of like a billion?
Yeah, so we'll be covering that later on of like what is a sufficiently large sample size. And you'll notice a lot of surveys do 1,500, like the Gallup poll does 1,500, the GSS does 1,500, and so there's a reason for that. So yes, Brittany.
If there's 500 in the bag, wouldn't you get the same sample?
Ah, very good. You're a step ahead, but you're understanding it. So we're sampling from this bag, we're taking a sample of 500. To generate a sampling distribution, we can take repeated random samples from this population, which is actually equivalent to the larger population. Thus, we can draw 1,000 plus samples from this. Now, I'll get to Brittany's point. But won't all of the subsequent samples of size 500 we draw from this bag produce the same sample statistic as the original sample? So if I resample and pull out 500 out of here, what's my sample statistic going to be? 0.52. Well, how does that help us? Well, even when I pull out one Reese's Pieces out of this bag, it's no longer equivalent to the population. After I've pulled out about 100, it's losing its equivalency. So in order to maintain the equivalency is by sampling with replacement. So pretend this bag is equivalent to being that at the factory. We reach in, we sample one, a yellow one. So that's not orange. So in order to restore this bag back to being equivalent to the population, I note down I picked out one yellow one and then I put it back in. So it's back to being the population again. And then I pick my second one. Hey, another yellow one. And I put it down.
So you don't just go through and count all of them?
You don't count all of them, but you sample with replacement 500. After you've pulled out your 500th Reese's Pieces, the sample proportion is going to be different.
Okay.
It's going to be pretty close, but it's going to be different because it's randomly sampling. And so the discovery that occurred was we can do this if we sample with replacement. So that kind of walks you through the logic of what they're doing when they're doing bootstrapping, and it's really important to understand it, how that works. And so you can read what's in the book, and you can also read what's on these slides to begin to get your mind around it. Or you could do your own test. You could go up to Hershey, Pennsylvania, and sit there and compare the two experiments. And as I demonstrated, after we sample a unit, or a Reese's Pieces, we put it back into the population such that each unit can be selected more than once. So basically you want to make sure that everything in this bag, each time you pull out one, has an equal chance of being selected. Because if I didn't put it back in, it would no longer be equivalent to the population. So by sampling with replacement, we can ensure that the population in the bag retains the same proportion of orange pieces that are in the larger population. This type of sampling process is known as bootstrapping. Bootstrapping terms, they're similar to the terms we've been looking at, but they're slightly different. A bootstrap sample is a random sample taken with replacement from the original sample, and it needs to be the same size as the original sample. When Tim pulled out his 10, he had a sample. From that, we could generate bootstrap samples. You want to be able to differentiate from your original sample compared to your bootstrap samples. And then for each bootstrap sample, you can find a bootstrap sample statistic. Just like with our original sample, we have a sample statistic, then for each bootstrap sample, you can compute the bootstrap sample statistic. When you do it 1,000 times, you're going to get a bootstrap sampling distribution, and it's the sampling distribution of many bootstrap sample statistics. So what we did yesterday was did the more expensive way, doing multiple samples, writing down the sample statistics and then creating a sampling distribution. But in reality, it's not economically feasible to do that. And so instead, we generate bootstrap samples with the goal of ultimately getting a bootstrap sampling distribution. Because we couldn't do it on our own by doing 1,000 different samples. We did it the more efficient way, which is the bootstrap method. So that's all text. Here's a visual way to look at it. We have our original sample. If we say it's the Reese's Pieces, it's the bag of Reese's Pieces. And then we have a sample statistic which is 0.52, which is in this bag. We need 1,000 samples of 500. So we do 1,000 bootstrap samples, and there's computer programs that do this. So you don't actually have to sit and pull out. So we generate 1,000 plus bootstrap samples, and then for each bootstrap sample, we calculate the bootstrap sample statistic, and then what it produces for us is a bootstrap sampling distribution. A quick sidebar, why is it called bootstrapping? You've probably heard the term pull yourself up by your bootstraps. It's lifting yourself up into the air simply by pulling on the laces of your boots. It's a metaphor for accomplishing an impossible task without any outside help. We have one random sample, that's all we have. How can we generate 1,000 random samples using this one sample? So I said there's technology that does this for us. The one that we'll be using is found at StatKey, and I'm going to show you how we would do this. But you guys are going to have to do this too, so watch, and then I'll have a slide at the end of the lectures where you can see what I've done. What this website is, the types of variables you're looking at, so if you're looking at one quantitative variable, it's this row, one categorical variable is this row, and eventually we're going to be comparing quantitative with categorical and comparing two categorical variables and two quantitative variables. With our Reese's Pieces, what type of variable is it that we're measuring with Reese's Pieces? Is it a categorical variable or is it a quantitative?
Quantitative.
Why is it quantitative? So when we pull out the Reese's Pieces, we're putting it into one of three buckets. We're either putting it into yellow bucket, brown bucket, or orange bucket. Because there's buckets, that would imply that it's more categorical. Even though we're generating quantitative statistics from it, what we're measuring is color, like you said, which is more of a category. Versus if we were measuring size, that would be quantitative, because then we would have like 3 centimeters, 3.2 centimeters, 2.9 centimeters. So because it's a categorical variable, we go here and we click, and then it pops up this screen. Then the way that we do this is you just go to Edit Data, click on that. It says, please select the values for count and N. So count is the number of orange Reese's Pieces. So what did you say, Tim?
260.
Yep, so from our original sample, what was the number of orange Reese's Pieces? And then N would be what? 500. That's our sample size. So basically we're entering in the information from our original sample. This is the one sample we have. It was a sample size of 500 and 260 of them were orange. So then we put in 500. And what this program basically does is it simulates sampling with replacement. Let's do one bootstrap sample. And what's the sample size of this bootstrap sample going to be?
500.
500. Okay, so let's do it, see what it does. So here's our original sample up here. Count was 260, sample size was 500, the proportion was 0.52. So in our bootstrap sample, when it did sampling with replacement, the count of orange pieces was 257. Sample size is still 500, and then the sample proportion is 0.514. Well, let's do one more. It's slightly different. The count was 258, 0.516, and so if you see down here, we did 1, 2, and then boom, we did 1,000, ran it, the simulation 1,000 times. And so what do each of the dots on here represent? What is this x-axis? It's the bootstrap sample statistic. There should be 1,000 dots on here right now. If this is a collection of all the bootstrap sample statistics, what's the name of this distribution?
Bootstrap sample.
Excellent. The bootstrap sampling.
Well, that's the final answer.
Yes. So our goal was to generate a sampling distribution, which is a collection of sample statistics. The way we're doing it here is by generating a bootstrap sampling distribution. What is it that we're interested in when we're looking at a collection of sample statistics? What is it that we need to find out about the sample statistics? Brittany?
Standard error.
Yes. So the whole reason why we're generating this is when we started, we only had one sample statistic. That's a good point estimate for the population proportion. But how much does this one statistic vary? You know, if we did the sample again, how much would it vary? Because we want to know what's the range of plausible values. And so by doing this, we get a bunch of sample statistics, what we're interested in knowing is what's the spread of this distribution. And what's our primary way of measuring the spread of a distribution? Standard error. Standard deviation, and for these types of distributions, it's called a standard error. And so if you look up right here, this gives you the standard deviation. Like I said, you won't have to do the math, you won't have to use that formula. Most of the stuff that we'll do will give you the standard deviation. The whole reason why we're walking through this whole process is so that we can find how do the sample statistics vary, and ultimately find out what's the standard deviation of the distribution of sample statistics. The variability of the bootstrap statistics is similar to the variability of sample statistics. I wish I would have kept the Reese's Pieces, the one on the computer where it dropped 1,000 Reese's Pieces into a thing. The standard deviation for that was very similar to the standard deviation we got through bootstrapping. Whether you did it in actuality where you did 1,000 samples and calculated the standard deviation for the sample statistics, it would be more or less the same as what you get from using the bootstrap. So they've actually tested this to prove that bootstrapping works. You can actually run the impossible of doing the 1,000 experiments and then compare it with the bootstrap. And if the numbers are close enough, you're like, wow, bootstrapping actually works. So the standard error of our sample statistic can be estimated using the standard deviation of the bootstrap sampling distribution. So based on this sample, give a 95% confidence interval for the true proportion of Reese's Pieces that are orange. I'm going to let you guys try and do the math. Does anyone think they know the way to calculate it from this? You will have a cheat sheet so you can write down these formulas, but in my experience, if I just write down tons of formulas and don't know why they're used for what, it's actually more confusing. So look at questions like this that are on the slides or in your assignment and say, okay, when they're asking about 95% confidence interval, this is the equation. And we'll go through other examples. But you start with your original sample, that's your sample proportion, which is 0.52. And then you use the information from the sampling distribution, in particular the standard deviation, to calculate this part of the equation. Bootstrap distribution. You have a sample size of 500, and you sample with replacement 1,000 times to get 1,000 bootstrap samples. That's what we just did. What is the sample size of each bootstrap sample? Is it 500 or 1,000? You're right, it's 500. Why do you say 500?
Because you're constantly replacing them, so.
Yes. And a characteristic of a bootstrap sample is that it needs to be the same size as your original sample. So you have a sample size of 500, you sample with replacement 1,000 times to get 1,000 bootstrap samples. How many bootstrap sample statistics will you have? Brittany?
1,000.
1,000. Why?
Because you ran 1,000.
Yep, you've gotten 1,000 bootstrap samples, then you're going to calculate 1,000 different bootstrap sample statistics, and then that's what creates our sampling distribution. How many dots will be in a dot plot of the bootstrap sampling distribution? 1,000. Each dot in the bootstrap sampling distribution represents a different sample statistic. Okay, so we're going to do another example to solidify this. The question is, what's the mean commute time for workers in Atlanta? What type of variable is this? Is it going to be a quantitative variable or a categorical? Chelsea, why quantitative? Okay, exactly. So with Reese's Pieces, it was categorical, so we're looking for proportion. With this, it's commute time, which is quantitative, and so we look for the mean. So then this is a random sample of 500 commutes. So they went to Atlanta, they did a random sample of 500 people, and they said, how long do you take to commute to work? And then this is our random sample of 500 commuters, and this is measuring their commute time. So this dot plot, is it a distribution of commute times, or is it a sampling distribution? The dot plot is either a sample distribution or a sampling distribution. Which one do you think it is? Chelsea says A with 60% confidence. So it's the distribution of values from our sample. So this is our original sample, n equals 500, the mean is 29.11, and then the standard deviation is 20.72 minutes. And what is standard deviation measuring? The mean measures the center of the distribution, and the standard deviation measures what? It measures how spread out, the spread of the distribution. So standard deviation measures spread. So then the mean is 29.11. And so that's our sample mean, McKay. If I wanted to estimate what the population mean is, the mean commute time for all people in Atlanta is, what would be my best estimate? Yes. So our sample statistic is our best estimate of what the population mean is. But it's a point estimate, and so then you kind of want to ask, well, how confident are you in that estimate? And so then the confidence interval for the point estimate is what for this? How do we calculate confidence interval? B. Okay, and how did you calculate that?
It's like we did before, it's 2 times the standard deviation, and we add or subtract it. And then
So we'll do the sample statistic plus or minus 2 times standard error. So yes, SE, what does that refer to? Standard error. And so for this half of the equation, we use the sample statistic. For this half of the equation, this right here is the standard deviation of the sample distribution. That tells you the spread of the sample. But when we're calculating confidence interval, we want to know the standard deviation of the sampling distribution. This wasn't even really a fair question because it's confusing, because you did it exactly right, but it's a common thing to get tripped up on. It's like, oh, okay, mean, standard deviation, boom, I figured it out. But, and this is where the trick is, you need to find the standard deviation of the sampling distribution, which is the distribution of all the sample statistics. Because we only have one sample, this is only one sample statistic, and in order to figure out the confidence interval, we need to know how the sample statistic varies from sample to sample. So I'll affirm you in that you had the right equation, but then it's important to know which pieces go into the calculation. Yes, Chelsea?
When do we use,
So that's good. This value right here, 2 times the standard error, is the margin of error. So that's just the term for that. So it's the same thing. But you can't just say, what's the margin of error? You need to know, how do you calculate the margin of error?
Okay.
And it's 2 times the standard error.
I got confused last
Yeah.
time doing that because I was getting the same thing, but I didn't realize it was
Yeah.
calculated.
Rachel, how can we determine the variability of the sample statistic so that we can calculate the confidence interval for the population parameter? How can we find out how this sample statistic, the sample mean, varies across samples? So this is our original sample, and we got one sample statistic, but we need 1,000 sample statistics so that we can find out how the sample statistics will vary across samples. What are ways that we could gather another 1,000?
So doing like the bootstrap?
Yeah.
Okay.
Or we could go back to Atlanta, grab another 500 people, grab another 500 people, another 500 people. But instead, we'll do a bootstrap distribution using the original sample. What type of variable is this? Quantitative, right here. And so we go right here, the confidence interval for a single mean, and then it pops up this. Because this is one of the data sets that's already in here, we can just go right down to it where it's Atlanta commute times. What do you notice this being right here? Well, it says it. It's the original sample. N of 500, mean of 29.11. Then what we're going to do is, that's our sample. We have, and actually you can look at it. Here's the actual data. These are all commute times for all the people in Atlanta. So you can kind of think of this as the Reese's Pieces bag, except for in the bag, instead of it being Reese's Pieces, it's balls with numbers on it. 20, 20, 20, 20, 40, 40, 30, 30, 40, 40, all the numbers. So it's like, to do the bootstrap, we're going to reach into the bag, pull out a ball. It's going to have a number on it. That's going to correspond with a commute time. We're going to write that down, put the ball back in, reach in again, look at the number, write it down. So it's going to generate a bootstrap sample. We'll do one sample, and let's see, let me pull this. If you look here, here's the bootstrap sample. Sample size is 500. The mean commute time for this bootstrap sample is 27.728. And then the important thing that we find is the bootstrap sample mean, and we put it down here to start creating our sampling distribution, because we need to know the standard deviation of the sampling distribution in order to get the confidence interval. It's exactly what Rachel was doing. She was saying sample statistic plus or minus 2 times standard deviation, but it's the standard deviation of all these sample statistics. And so we'll do it right here. We'll generate 1,000. So this gives us our distribution of sampling statistics. We can then look at this important value here, which is the standard deviation. So,
I'm confused on like the last part.
okay, with this part?
Yeah.
So there's 2 things going on. This is our original sample, and it has a mean and a standard deviation. The standard deviation right here is measuring the spread of these values, which is important for like different analyses that you do. But when calculating the confidence interval, what we need to know is what's the distribution of sample statistics. And so we want to know the standard deviation of this distribution. So this is just one sample with one sample statistic, whereas this is 1,000 samples with 1,000 sample statistics, and it gives you the standard deviation of the sample statistic. And that's where this one is also called standard error. That could even be a helpful way for you to think, don't use the standard deviation of the original sample, use it of the sampling distribution. So if you're going to give me the confidence interval for commute times.
Use 0.954.
Exactly.
Okay.
We put it in 0.954. So this is basically a replication. And then the confidence interval is what Rachel had said. Now, one thing that you'll notice is that, like here, with this example, the standard deviation is 0.915, whereas on the one that we just had on the computer, it was like 0.954. That's because these are random samples, so they are going to vary a little bit. So don't be freaked out when, like, wait a minute, it's like I'm off by 0.04. That's okay. Being off by 0.04 is okay, and it's just indicating that because these are random samples, you're going to have some variation. Okay, so then we've been talking about confidence level, confidence interval. The 95% confidence interval, so this is our sampling distribution, and we want to know the 95% confidence interval. It's the point estimate plus or minus the margin of error, which is what Brittany was saying. Another way to say it is the sample statistic plus or minus 2 times the standard error. And then another way to say it is the sample statistic plus or minus 2 times the standard deviation of the bootstrap distribution. All these things are the same, but depending on where you read it in the textbook, it might say it differently. So that's why I'm just sort of spelling it all out. They're all saying the same thing, but they're using terms interchangeably, which doesn't help. Then the way you calculate it is you get your sample statistic, which is up there, and then you pull your standard deviation of the bootstrap distribution, which is right here. So what you don't want to do is the standard deviation of the original sample, nor do you want to use the mean of the bootstrap distribution. So you'll have this slide so you can kind of know where we're going. The beauty of bootstrapping, we'll have to wait till tomorrow.